Right, so we're back for part 2, which will be on rancidity, something which we may or may not be familiar with. Rancidity is a breakdown of fats and oils leading to unpleasant smells and off flavours. So if you leave the butter too long in the fridge, this is what will happen to it eventually. And also your olive oil, particularly if it's stored in glass containers and kept in sunlight. There are two main types of rancidity: lipolytic, where free fatty acids are released, often by enzymes. The free fatty acids are quite smelly. And oxidative, which is often initiated by free radicals, of which more in a while. We notice that lipolytic has some good benefits to it. It's essential for cheese, whereas oxidative is almost never a good thing. It's an indication your food has gone off. We refer again to the sadly missed Nordic Food Lab, which has a big section on aged butter, and it's well worth having a read if you're interested in this. There's a picture of smen there from a Marrakesh souk. In Morocco, smen, or as it's called in French, bourrée rancé, is highly prized. It's made by mixing normal butter with herb-infused water, often with oregano, leaving it overnight, straining, and then aging for anywhere between a couple of months and several decades. An oft-recorded story is that families would make a batch of smen on the day their daughter was born and only open to stir it through the ceremonial couscous on the day of her wedding. Again, lots of good stuff as this, as I mentioned, in the Nordic Food Lab, what remains of it. So breakdown points is typically how triglycerides are broken down by two processes: by hydrolysis of the ester bond, often by an enzyme, or by oxidation, often involving double bonds and the carbon atoms next to double bonds in the carbon chain. Lipolytic rancidity is probably the most common in domestic situations. Enzyme present in food successfully hydrolyze the ester bonds to the carbon chains, releasing diglycerides, monoglycerides, free fatty acids, and ultimately glycerol is shown in the process there. Here are some examples of the free fatty acids released by common foods. They all have quite distinct odours, and whether they're pleasant or not often depends on the concentration, it has to be said. As I mentioned, it's not always a bad thing. In cheese making, such hydrolyses can produce desired flavours and contribute considerably to the complexity of the flavour of cheese. Again, the production of small volatile molecules is associated with the characteristic flavours of different cheeses. If you're interested in more, there's plenty online. There's a reference in the notes. Okay, oxidation reactions in food, which is a complex area. So I'm going to give an overall review of this. Oxidative rancidity, as mentioned, is always a bad thing. And as you might expect, based on the name, it is promoted by the presence of oxygen. Often produces volatile alcohols and ketones and other small molecules, which may smell quite unpleasantly, as our friend here is indicating. These volatile aldehydes and ketones produce unpleasant smells and flavours, so reduce consumer acceptability. Oxidation can also cause proteins and lipids to bind together, making them less digestible, so reducing nutritional quality, something we've talked about in another lecture in this module. Okay, so oxidation and possible mechanisms. It can be caused by free radicals normally present in food, and it's promoted, that is to say, the rate is increased by heat, light, and some enzymes. We're going to concentrate mostly on, photo-oxidation type ones initiated by ultraviolet light, causing a free radical reaction to take place. Okay, so free radicals. You may have done this before in biochemistry. Free radicals are when a molecule has an unpaired or spare electron. This is not the same as a negative charge. It makes such a species highly reactive and short-lived. Free radical damage to proteins and lipids is often of significant concern in food processing and food storage in the medium to long term. And the point that I've highlighted is it's very reactive and can cause chain reactions. So once you get the process starting, it can accelerate quite rapidly. All free radical processes involve these three stages: initiation, propagation, and termination. The free radicals are typically produced by normal metabolic processes such as mitochondrial electron transport, which you've probably done in human metabolism, some of you anyway, and by exposure to X-rays, ozone, cigarette smoking, air pollutants, industrial chemicals and a range of other things. In the propagation stage, atmospheric oxygen reacts with a normal species to produce highly reactive free radicals and then even more reactive peroxy radicals, designated ROO star. These react with unsaturated fatty acids to produce hydroperoxides, ROOH. These act to regenerate a radical, and this can restart the process and produce a chain reaction. Note that the hydroperoxide group is not the same as the carbonyl group. Eventually, enough free radicals may be present to terminate the reaction by reacting with each other and to produce non-radical products in termination reactions. Now, the health consequences of oxidative stress are beyond the scope of this module. If interested, you should read further around. I mentioned Lobo et al., which is included in the background reading. Okay, we'll look at this in a little bit more detail now. Right, but first a little bit of stuff about photo-oxidation. Now, I haven't talked about oxygen now designated as singlet oxygen. There's a couple of states of oxygen. The normal state is referred to as triplet oxygen. And I don't think you've done enough on the energy states of particular atoms for us to consider that here. So what happens is that the molecule gets energy and it becomes what's called a triplet. It becomes what's called the singlet state of oxygen rather than the more stable triplet state. So I'm going to move on after that. The systems most relevant to food involve the production of singlet oxygen, which when oxygen reacts with pigments such as chlorophyll and riboflavin, which is important in the deterioration of fresh milk. As I mentioned, the singlet state of oxygen is high energy. The reasons for this, as I mentioned, are a bit beyond the scope here, but once you've got the oxidative damage, it can go on to damage lipids, proteins, DNA, and lots of other things. Yeah, so the singlet state of oxygen. And now this is the process summarised in two ways, one chemically and one in words, and I've got 3 slides here which go through each step by step. So in the initiation phase, free radicals, as I mentioned, are a very reactive species that have a spare electron, which makes them very reactive indeed. If they encounter a lipid, for example, the lipid will lose the hydrogen to form water. It typically loses the hydrogen next to a double bond or adjacent to from a carbon adjacent to a double bond. Becomes a lipid radical, which again is highly reactive. So here we have the initiation. We've gone from a free radical, such as the OH radical, to a lipid radical. Notice the unpaired electron designated here and here. Propagation involves the reaction of this lipid radical with another unsaturated fatty acid in this case, but it could be DNA, it could be protein, it could be a range of other things. Although often described as a chain reaction, this is more like a cascade reaction where one free radical produces 2, itself and a new one, and then these can go on to produce more free radicals. I guess you could say in the sort of context of things people talk about these days, it's R rate, it's more than 1. Termination, as mentioned, often arises when 2 free radicals react together, producing non-radical products, which can be a good thing or a bad thing. Generally speaking, a bad thing in terms of food, but it does stop the process from happening. So there we are. That's the process described both in chemical equations and in words. Yeah, oxidative rancidity, enzymic oxidation, involves non-heme iron-containing enzymes, which is lost. Your liver is brown because of these such enzymes. And the oxidized unsaturated fatty acids. There's a good video here which you should look at watching your own time. We'll take you through. And there's an example of one of the enzymes that does this. Deep in the heart of that somewhere there will be an iron atom. Okay, so antioxidants. We've got a question. As usual, pause the video while you think about it. Which foods are likely to contain antioxidants? Well, perhaps you should say which foods are likely to contain the most antioxidants. So pause the video. Need to bring them in. Sorry. Yep. So from these foods, which ones contain the most antioxidants? Right. Okay. Maybe not what you think. Although fruits contain antioxidants, you'll probably find more in processed foods like these, where they're added to reduce the rate of oxidation in these products which have high lipid concentrations. these products. Mayo is a typical example containing E320 butylated hydroxyanisole, which consists of 2 isomers, 2 BHA and 3 BHA, which are good antioxidants, and they do make the mayonnaise last longer. It also contains stabilizers, as we've talked about probably before, in terms of emulsifiers. Okay, so a little bit of stuff on a somewhat nebulous concept, free radical quenching. This can be defined as any reaction which the free radical forms products are not free radicals. It can be a complicated process, but essentially involves transferring the excess energy from singlet oxygen to a carotenoid free radical with a radical electron. So this over here is singlet oxygen, and this is the normal state of the oxygen triplet. The 1 and 3 relate to the arrangement of electrons, which I've said is a bit outside the scope here. Since carotenoid is a long chain of conjugated carbon atoms, the energy of the radical electron is dissipated as heat as it moves into the sea of electrons of the conjugated system. So hopefully we have so the extra energy is dissipated as heat. So this long chain of double and single atoms effectively contains a long chain of electrons which can move back and forth. So the radical electron joins this, and eventually, if you like, it just gets averaged out. Its chemical energy is dissipated as heat energy in this system over here. So these are good quenchers. They have long conjugated chains, which is why such molecules are said to be good antioxidants. So anything around 9 or more conjugated double bonds falls into this category. As mentioned, antioxidants can be used to extend the shelf life by extending the period before the onset of rancidity. So lard, for example, contains about 0.1% of BHA. It extends the shelf life by about a month, compared to a few days without this antioxidant being added. Another reason why things can be stabilized, why does butylated hydroxyanisole stabilize it? Because it has an aromatic ring system. I'm sure you remember this from biochemistry. In this case, the electrons in this ring are delocalized. We sometimes draw it not as 3 bonds, but as a ring. As you may recall, as I said from biochemistry, electrons in an aromatic system are delocalized. And in a similar way to the antioxidant action of carotenoids, the radical electron's excess energy is dissipated in the conjugated system, again probably as heat. It eventually just doesn't have enough energy left to propagate a free radical reaction. Enzymes can of course be denatured by heating, such as the tempering process used for soybeans as discussed earlier. So we moved on a bit from oxidative, especially with free radicals, to oxidation caused by enzymes such as lipoxygenases. So it considerably decreases the lipoxygenase activity. Okay, we'll pause there, we'll come back for the third part.